epoxidation. What is epoxidation? So what does the word per mean? Like perchloric acid. Miles per gallon. Per means over. So when I have a peroxyacid, it has more oxygen. Like you have permanganate ion, and then you have permanganate ion. You have sulfate ion, then you have persulfate. Persulfate must be SO5 minus. So it turns out if we take a carboxylic acid and treat it with peroxide, we can get a peroxyacid. So here is a peroxyacid, and here is an alkene, and here is this thing called epoxide. And then we get our carboxylic acid back out. Can anybody tell me what JB Weld is? Nobody can tell me what JB Weld is. All right, well, possibly if you're a guy, you break a lot of stuff, you have to glue a bunch of stuff. It's a form of epoxy glue. We'll look at that later. And the epoxy glue has an epoxide in it. So an alkene reacts with a peroxyacid to form an epoxide, also called a oxyarane. The most common peroxyacid used is metachlorobenzodic acid. That's a mouthful, so we say MCPBA. In lab, you've worked with BA, benzoic acid, extracting it, recrystallizing it, measuring its melting range. So here's a carboxylic acid that has one extra oxygen, so we call it a peroxyacid. These electrons grab that oxygen, those electrons jump down, and we get this weird transition state. That goes away, this pops back off, and we get our carboxylic acid back, and we produce the epoxide and a molecule of acid. So here's our metachlorobenzodic acid. Wow, this looks like some stereochemistry here. Here we have the cis isomer of 2-butene, and of course we get this 3-membered ring, epoxy ring. Here's the trans, and so we can see that difference here. These lines are in the plane of the board. These wedged lines are coming out at us, so we see that stereochemistry occurring. So what are the cool thing about epoxides besides JB Weld being able to fix a lot of stuff? Well, organic chemists use epoxide rings to then do further chemistry, opening the epoxide ring. So this is acid-catalyzed. This oxygen gets protonated. Now notice it's kind of like a good leaving group. Another water slams into that carbon there. The oxygen leaves, and then more water pulls this hydrogen off, and we get what we call a diol. 2 OHs on the same molecule. So we might call this a trans-cyclopentane 1,2 diol. And if we look at this, we could probably draw a mirror image. That means it has an enantiomer. Like instead of the water hitting here, if it hit over here, we'd probably generate the mirror image. And so there's equal probability, so we get a 50-50 mixture of these two enantiomers. And what is the stereochemistry? We say it's a kind of like an anti-addition. We say an anti-diol is formed in that the OH, one's on the lower side of the ring and the other is on the upper side of the ring. So here's a peroxybenzoic acid. Here's peroxyacetic acid, and we can see a little better yield with this one. And this one was a first one, metachloral peroxybenzoic acid. Now what had me a little bit confused is this thing, and this thing look about the same, but they're stopping here at the epoxide level, and they didn't go ahead and bust it apart. Here we would form this thing, and then we bust it apart and get this meso compound. So how does hydroxylation differ than anti-hydroxylation? That would be what we just saw with busting apart an epoxide ring with aqueous solution, acid-catalyzed aqueous solution. So here's osmium tetroxide and peroxide, and we get a diol just like before, but it is not anti, it's a syn addition. An alkene is converted to a syn 1,2-diol, and we have two reagents. We have this osmium tetroxide, and if you find osmium up there on the periodic table, it's 2 rows below iron. It is kind of a nasty, toxic, heavy metal. And here, potassium permanganate. That means it has one more oxygen than just the manganate anion. But if we have a cold solution and keep this dilute in base, we get a syn diol, 1,2-diol. So why do these reagents give us a syn addition? Well, this thing looks flat and planar to me. It must be an octahedral system. And there's the alkene. You get this osmate ester. Then you add the peroxide. And there's the glycol, which is another thing 1,2-diols are called. You might have heard of ethylene glycol. It used to be used as coolant in your radiator. It's toxic to pets, turns into oxalic acid. So nowadays a lot of antifreeze is propylene glycol, not quite as toxic for pets. Why do pets like it? These OH groups are like a sugar molecule. A sugar molecule has all these OHs, makes it sweet. So the cat comes and sees this neon green stuff there on the garage floor, starts licking it, tastes sweet. They go to town. Not a good situation. The osmium tetroxide adds to the double bond of an alkene in a concerted manner. Concerted mechanism, that means all at once. And you get this osmate ester. And then hydrolyzed. That might mean to like split with water. And then you produce a cis glycol. And you get your osmium catalyst back. The permanganate dihydroxylation. Notice how similar the permanganate ion is to the osmium tetroxide. Looks flat and planar. Probably an octahedral system. And here you can really see the syn addition where your hydroxides are on the same face of the ring. And we use a cold dilute solution of potassium permanganate. Does the same thing. Hydroxylates the alkene with syn stereochemistry. And you can see the system turns basic, and we get this beautiful chocolate brown manganese 4 oxide. And this must be a common name because we generally use the Greek prefixes for molecular compounds. So in a couple weeks, our last lab of the semester, can you believe that? You're going to take the product that you make today and do an oxidative cleavage with potassium permanganate. It says if the solution is warm or acidic or too concentrated, oxidative cleavage of the glycol may occur, and the di-substituted carbons become ketones, monosubstituted carbons become carboxylic acids. So osmium tetroxide is expensive, highly toxic, volatile. That's bad with the toxic thing. It goes in the air and you breathe it. You got to keep it in a hood. This stuff you can do out on the bench top. Looks like I doubled up on slides or something. Sorry about that. So here is an alkene. So notice it doesn't say cold and dilute. So we form the glycol, but then there's more of this, and the warm condition, this bond gets cleaved, and this is an oxidizing agent. The manganese is in the +7 oxidation state. So it wants a bunch of electrons. And so here is a ketone, and here is an aldehyde. So that last couple slides ago said, oh, we get ketones or carboxylic acids, and it said some stuff about disubstituted gives you the ketone, the monosubstituted gives you the carboxylic acid. So the ketone and acid, the way you want to think about it is, if you were to chop this double bond in half but keep it around and put oxygens on there, that would be your products. Now this thing gets oxidized to the carboxylic acid real quick like. So this is never isolated. It occurs and then it quickly turns into this. So notice here's a double bond. So when I try and figure out what my products are going to be, I look at this and I say, if I chop that off and put an oxygen there, I'm going to have that ketone. And then I look here and see that I have a hydrogen, and I say, okay, I'm still going to chop this off and put an oxygen here, but then I'm going to have an OH here and get that carboxylic acid. Now look at this interesting thing. I have a double bond here and a double bond here. This one I'm going to chop off and put an oxygen. There's the ketone group. Since I have a hydrogen here and a hydrogen there, when I chop this off, I'm going to put oxygens there. Well, can't see it. They gave us a condensed structure. But we have oxygen double bonded to carbon, and then we have an OH. Like up here, we have oxygen double bonded to carbon, and then we have an OH. That's what's there. This thing here is the CO2. How many of you know what ozone is? O3. Is it good to breathe? Is it good to have in the atmosphere? Protects us from UV light when it's in the upper atmosphere. But it is not a good thing to breathe because it's reactive. And this thing cleaves things just like potassium permanganate. But wow, look at this temperature. This is nice and cold. This is like liquid nitrogen level cold. So ozone oxidatively cleaves, breaks the double bond to produce aldehydes and ketones, depending on how this is substituted. If we have two alkyl groups, we get the ketone. If it's only has one alkyl group and a hydrogen, we get the aldehyde. And it's a two-step situation. This dimethyl sulfide turns into that thing called DMSO, dimethyl sulfoxide. So this acts as a reducing agent. Here's the alkene, here comes the ozone. You know, it just looks bad. We've got an oxygen with 3 bonds, an oxygen with 1 bond, and we get this 5-membered ring. It rearranges to an ozonide. I don't make you learn any of these names. What I make you learn is what the reagents do. So a lot of draw the structure of the product type questions. So here's the ozonide, add the dimethyl sulfide, breaks this all apart, and we get our ketone and our aldehyde. So 2 reagents that do the same thing. Why would you choose one over the other? I would choose this one because we got it in lab and it's easy to do. This looks a little tricky, but many times people choose the ozonolysis because it stops at the aldehyde state. If we're needing an aldehyde, we can get it. If we want an aldehyde right here, we're not going to get it. We're going to get the carboxylic acid. Any questions? No questions?